examination of Block 3 clearly demonstrates this is not just simply an upgrade of the D model, but essentially a new aircraft with integration of many advanced technologies that greatly increase the system's lethality, survivability, and overall operational effectiveness, and extends Apache's service life well beyond 2030. Block 3 is a major success story on how the proactive Army Aviation Science and Technology program operated in close coordination with the Army Attack Project Manager's office so that a major enhancement of a fielded system was achieved through effective technology insertion. With that in mind, let's examine the most important technology transition events leading to this exceptional weapon system. Central to Block 3's success is its total propulsion system made up of a new engine, upgraded transmission, and an advanced rotor blade. Collectively, these add up to an operational gross weight increase of approximately 500 pounds, but at essentially no increase in empty weight. In other words, the Block 3 has 500 pounds more useful load that can be used for significant increases in range and endurance, as well as addition of new features such as survivability enhancements and mission equipment, which will be discussed later. Achieving this load increase was a direct result of three major AMRDEC S&T initiatives. Let's start with the T700GE701D engine. Working with the Navy and Air Force in support of the OSD Integrated High Performance Turbine Engine Technology, or HIPTET, the AMRDEC conducted the Joint Turbine Advanced Gas Generator, or JTAG program, which demonstrated major advances in power-to-weight ratios and specific fuel consumption for a next-generation engine. However, it was clear that several of the JTAG technologies that had proven themselves in fielded commercial engines were candidates for selected improvements of the T700GE701C. The AMRDEC worked with the PEO Aviation and General Electric to insert an advanced combustor, improved turbine cooling techniques, new single crystal turbine nozzles, and advanced thermal barrier coatings that collectively led to a 5% increase in shaft horsepower, and did so with no increase in engine weight. Although the increased power helped overcome some performance limitations, its full value could not be realized without a corresponding improvement in the Apache transmission and rotor, and the PM and AMRDEC had a strategy for this. About 20 years ago, the Army Research Labs Propulsion Directorate conceived a concept known as face gears for turning the corner between the horizontal orientation of an engine and vertical for the main rotor transmission. Face gears were potentially less expensive than currently used spiral bevel gears, and also offered the ability to split the torque between two output gears, thereby lowering total transmission weight. The critical path to getting there was elimination of surface pitting, which required advancements in gear materials, grinding technology, and achieving critical tolerances in assembly. Teaming with ARL, the AMRDEC incorporated the split torque face gear technology into its advanced rotorcraft transmission, or ART program, which further demonstrated the value of these technologies and led to the AMRDEC follow-on effort, Rotorcraft Drive System 21, or RDS 21. This was further accelerated by a CRADA with Boeing and Northstar Aerospace, where the AMRDEC orchestrated an effort to design, manufacture, assemble, and test an Apache-size advanced split torque transmission, which also incorporated several additional technologies such as super finishing of gears, advanced lubrication oils, and hybrid ceramic bearings. Extensive testing clearly supported projections of 25% increase in power throughput with essentially no increase in weight. Furthermore, a 50% decrease in O&S costs was also projected due to a major reduction in parts and far greater component service lives. RDS 21 led directly to the Block 3 transmission design, which achieved the goals of no empty weight increase over Block 2 while increasing reliability and durability. Now, Block 3 could increase power available from T701D to the rotor system. However, the existing rotor had major limitations in effectively absorbing the increased power and thus the third technology area. Boeing, in conjunction with the Attack Project Manager's Office, initiated design and development of a new rotor blade for Block 3 based on rotor airfoil concepts conceived under DARPA's Affordable Apache Rotor program. Matching a new rotor blade design to an existing hub is a most challenging task, and it was quickly realized the PM Boeing team required design expertise available only in the AMRDEC if the program was to succeed. AMRDEC engineers worked seamlessly with Boeing to quickly and thoroughly analyze design trades for the new blade using advanced analytical tools recently developed under the Army Aviation S&T program. Additionally, Boeing took advantage of numerous materials and structural design concepts developed by the AMRDEC to develop a rotor blade design that provides a 3% increase in lift efficiency while decreasing vulnerability and significantly lower ONS cost compared to the original Apache design. The T701D engine, split torque transmission using face gear technology, and a new rotor blade, all keying off AMRDEC technology and technical expertise, produced a 500-pound increase in lift with essentially no increase in empty weight. Now that Apache was a better helicopter, AMRDEC turned to addressing how to achieve a more capable weapon system. It became evident in the early 90s that the Apache Block 2 electronics architecture, although much better than Block 1, had a number of shortcomings regarding growth potential to handle concepts like cognitive decision aiding and full manned-unmanned teaming. The AMRDEC studied a series of S&T initiatives with a consortium of industry partners that keyed off the Air Force C-130 AMP program and led to development and publishing of an open standard, which became known as the Rotorcraft Technical Architecture. This was followed by the AMRDEC supporting a Boeing-led effort to develop a Manned-Unmanned Common Architecture Program, or MCAP, which directly led to the Open Systems Architecture on Apache Block 3 today. MCAP employs a layered design with an Open Systems Gateway feature that readily allows continuous addition of new subsystems and features without the need of requalification of the full processor. Teaming with the AMRDEC, Boeing provided a Block 3 processor for extensive Army evaluations and demonstrations, leading to near real-time enhancements of MCAP during development and qualification of Block 3. MCAP is at least 3 times as powerful as previous designs, but also provides an architecture that has the flexibility of distributed systems, but the weight advantage of an integrated central processor configuration. MCAP is the backbone of the Block 3's ability to effectively operate on the digital battlefield of today and tomorrow. The AMRDEC recognized early on that teaming of manned and unmanned systems offered significant advantages for many aspects of both scout and attack operations, but it was a Cooperative Research and Development Agreement, or CRADA, starting in 1999 between the AMRDEC, Lockheed Martin, and Boeing that first demonstrated the potential. RPA Cognitive Decision Technologies allowed an Apache crew to control the sensors of a Hunter UAV and were the key to the success of this early effort, known as Aviation Manned-Unmanned System Technology, or the AMUST program. Major improvements in all aspects of target detection, engagement, and an increase in Apache survivability through reduced exposure to threat systems were demonstrated. Several Block 2 aircraft were equipped with a strap-on system for use in Iraq and Afghanistan and credited with many well-publicized successful missions. AMUST was followed by an expanded effort under a program known as Hunter Standoff Killer Team, or HSKT, which equipped 2 Apaches and Hunters and conducted numerous demonstrations leading to refinement of the technology and demonstrating a Block 3 could perform all the functions of a UAS ground control station, including firing weapons. It is important to note, however, this capability is only possible because of RPA cognitive decision aiding provided by the Block 3 MCAP-based processor. This effort is a vivid example of the AMRDEC's organizational teaming process for accelerated technology insertion. The AMRDEC's safety and survivability S&T efforts have provided basis for numerous improvements for the Apache and the rest of the operational fleet. Lightweight armor, fuel tank nitrogen inerting, and crashworthiness were key features for the A model and have continuously been improved during the Apache's operational life. Crashworthy and ballistic-tolerant external fuel tanks have provided increased endurance and range without compromising vulnerability. Maintaining the Apache's excellent crashworthiness, however, has been a major challenge. The Apache has grown in operational gross weight since fielding in the 80s, and additional growth with Block 3. This compromises the aircraft energy-absorbing features that is so important for crashworthiness. Recognizing this situation was present for the entire Army fleet, the AMRDEC initiated an S&T effort to perfect a concept known as high-performance shock strut, which utilizes a novel technique of fluid metering to increase the amount of energy absorbed by the components, such as the Apache landing gear, and does so with essentially no increase in structural weight. Once again, the AMRDEC teamed with Boeing and the PM for assessment of the concept, which led to full insertion into both Block 2 and 3, and fully recovered the excellent crashworthiness characteristics of the A model. Initiation and production and fielding of Block 3 has not stopped the AMRDEC technology transition for this system, and nothing shows this better than the highly successful Ground Fire Acquisition System, or GFAS. The AMRDEC initiated an effort known as Intelligent Decision Aiding for Aircraft Survivability, or IDAS, in 2008, aimed at demonstrating technologies for improving Army aviation ability to counter and kill threats such as manpads, RF-controlled weapons, and, more importantly, small arms and RPGs, which have proved to be the most lethal and ever-present. Because of increasing concern with ballistic threats, the PM tasked AMRDEC to lead a cooperative effort between the PM, Boeing, and a small business, Radiance Technologies, to quickly demonstrate a fully integrated camera-based system that not only warns the crew of incoming ballistic rounds, but automatically swings the targeting system and 30mm cannon to the threat's direction so that suppressive fire can be released in seconds. In other words, GFAS becomes part of the Apache fire control system as well as part of the aircraft survivability suite. Evaluations of the concept were so impressive that the PM has accelerated assembly of enough GFAS to equip a 1st Battalion of Block 3s headed to Afghanistan.